So we've got one more robustness kind of fact to prove, and then we're ready to build our universal Turing machine and close the book on uh, our model. We'll kind of have a fully kind of solidified, developed model to work with at that point. So we're almost kind of at the point where I want to get to. But the next thing we have to talk about is uh, multi-string machines, multi-tape machines. So remember we can have a one tape machine, and then I don't need to say that we have multiple tapes. So we want to prove kind of that you can always we want to think about simulating a multi-tape machine with one tape machine. Um, so that's kind of what we need to show that the number of strings is sort of interchangeable, and it's less interchangeable, and it's a little less trivially interchangeable. There's going to be some stuff about the complexity of the simulation that we're going to have to note very carefully, and I might put that in a separate video. This might be 2 videos long. So I'll just write down the theorem. Given a k-string Turing machine, k-tape Turing machine, I'll call it M. Whoops. Operating. Well, I'm not going to bother with the operating time yet. We'll think about the complexity a little later. Um, Given a k-tape Turing machine, there exists a one tape Turing machine M prime, which simulates M. Um, and so, obviously, I've said the word is equivalent Turing machine. I've said simulates. Really, what I mean, obviously, is that M prime is going to accept all of the same inputs. It's going to reject all the same inputs. It's going to halt whenever this halts. It's going to not halt whenever this doesn't halt, and it's going to give all the same outputs. It just does the same stuff. Um, so the proof is kind of fun. The proof is a little, I mean, it's fun as long as you don't go into the same kind of level of rigorous detail that we did with the alphabet size proof. And we aren't. Well, don't worry, we're not going to go that far. We're just going to kind of describe it. But I think you'll see that it's still rigorous. We've kind of said enough at this point that I can start to get more loose with my explanations and without you feeling ripped off or uncomfortable. So here's the idea. I'll start with the idea. We'll flesh it out more than this, but here's the idea, which is that we have multiple tapes, and by the way, maybe I should say this. Um, by previous result, we can assume for this that um, that all Turing machines, that all tape strings are one-sided. So we will be using the results of the last proof. And if you haven't noticed, we've been kind of, building one at a time. We've been kind of using each robustness fact to prove the next robustness fact. So for this one, we are going to rely on the last one, which said that, whoops, what the heck? Which said that then whether the Turing machine is one directional or two directional does not matter. So I'll put this here as a disclaimer. We're going to assume that we have a one tape machine. Um, so the idea, go away. Oh my God, I hate when it says this. If anybody has um, a suggestion of a different program to use, please let me know. I really am getting sick of this program. I see other people using all kinds of cool stuff, but I have no idea what it is. So anyway, here's the idea. We've got a multi-tape machine, and it's gonna have some stuff. I'll call it S1 maybe. We've got the cursor is somewhere. We'll deal with the cursors in a little bit. We've got multiple tapes, right? Dot dot dot. We've got K of them. Okay, so this is what the K-tape Turing machine looks like, and what we're going to do is we're going to kind of represent it this way. Um, we're going to represent it like this. One really long tape where basically we'll have a thing, and then we'll have a string s1, and then what we're going to do is we're going to close it off with a new symbol that we're going to add in. And then we're going to open it up again, and then we'll have another thing, s2. Oops, I should say s2. And then we'll close that off. And we're going to have basically markers for our workspaces. We're going to have multiple workspaces on one tape by labeling these special symbols that kind of indicate the end of one of the tape strings. And then you open it up again, and then you get the idea. Dot dot dot. Open up, sk, close it, and yeah, that's the idea. Um, so there's one complication here. You'll notice I didn't actually put any cursors anywhere. So what we're gonna do is we will have special copies of every symbol of M, which are which represent the symbol with if I'm using the special copy, it'll be like an underlined version of everything. And if I have the underlined version of the thing there instead of the actual thing, then the interpretation is that that's where the cursor is. So it represents the cursor position. Because what the issue here, remember, is that with a K-tape Turing machine, we have multiple cursors here. We've got a cursor here maybe, and a cursor here, and a cursor here, and they're all going to be doing their own thing. But I only have one cursor for the one tape machine, so I have to have special symbols to represent each cursor. So again, we're going to rely on that proof too. So this kind of uses everything. Um, so that's kind of the idea. So I mean, we'll flesh this out now. So to flesh out, alphabet will be this. So it will be sigma. This is sigma prime, the alphabet of our new machine, and it's going to be sigma, the old alphabet. Hold on, my cat just jumped on my desk. Calm down, please. So it's going to be that. It's going to be the old symbols plus the new symbols with an underline. So this is kind of the underlined set of all the symbols. I'll get into that in a second. And then we're also going to have, maybe I'll just write it in. Sigma here, sigma bar is equal to the set of all sigma underlined, such that sigma is in the. So it's a set of all symbols that are underlined. So if we've got like the symbol A in our old alphabet, then we're also going to have the symbol A with an underline in it instead of the new alphabet, and that's going to represent cursor positions. I shouldn't have erased that. And then finally, we're also going to have not just this thing, but a whole bunch of them. We're going to have also, uh, we're going to have two of these. They're going to have primes. We're going to have special ones. And then we're also going to have even specialer special ones. We've got the triangle prime. It's on the right with an underline over it. Triangle prime with an underline over it that's like that. And then finally, one of these that isn't primed or underlined. So, I mean, how many triangles are there? 1, 2, 3, 4, 5 of them. Quite a few, but you'll see that they're all kind of necessary. Um, but the basic idea is still this. You'll see how we need these to deal with some of the finer details, but um, don't worry too much about it. So first of all, let's deal with the initial setup. I'm not going to write down the states explicitly. There's going to be a lot of extra ones, and we're going to be using them in kind of a similar way to how we used the states in our proof when the alphabet was different, which is, and we used it. We've done this pretty much all the time, which is if you haven't noticed that you add states in to represent like your memory a lot of the time. A lot of the time, you'll add in more states to remember finite details of what you're doing, and so I showed you that explicitly with the alphabet size proof, and we're going to be making use of that again here, but I won't be writing it out explicitly. Um, so initial setup. So initially, M, the original machine M of X looks like this. We're going to have, we've drawn a lot of tape here today. There's a triangle, and then of course X. Remember, with the multi-tape machine, the interpretation is always that the top string is the input tape. and the bottom string is the output. But then this is, of course, blank, and everything else is blank. And so I'm going to actually kind of take a liberty here and assume that the cursor actually starts on the first symbol of x, even though I do have a thing here. That doesn't matter too much. I'm not even going to put the cursors. Oops. My point is that initially we have x in one string and then nothing else anywhere else. So um, while m prime of x will look like, the typical starting thing will, for a one tape machine, which is basically exactly like this, but with none of the extra tapes. So initially we have m prime looking just like the first tape here, but with none of the extra tapes. So we're going to kind of initialize the simulation by kind of creating those environments. So we need to create the environments for the tape cells. Okay, so step 0. I'm not going to call this step 0. So initialize the simulation by creating this. So before we do anything, we're going to start kind of doing, it's going to be similar to the alphabet proof in which I kind of describe how to simulate a single step. But before we can start to simulate the steps, I have to kind of create an initial setup to do the simulation. And so the simulation is going to look like it's going to look like this. So we're going to first of all, we're going to make a space in between this triangle and the actual string x. And we'll have to use our space creating algorithm for that, or space creating subroutine, but we know we can do that. And what I'm going to put here is a triangle, um, a triangle prime. Because and the reason I need this is because remember when we're thinking about unidirectional Turing machines, uh, we have some special conditions on this triangle, which are that the string our cursor can never go to the left of it, and it also can't erase it. And so because we're going to need to be messing around with these, I need to create a kind of a special prime version of it. This guy, it's still a unidirectional machine because I can't move to the left of this guy, I can't erase this guy, but these guys are just kind of pretend versions of them, and I'm going to need to edit them. So I have like a prime version of it, and then I have the string x, and then I have the closed off thing with a prime, and then I'm going to have this, and with a prime, and then it's going to be just closed off because there's nothing going to be, nothing is there originally. Nothing is there at first. Um, uh, yeah, and that'll be a prime, and then dot, dot, dot. And then finally, we'll have one more. And so there's k of these, or k minus one of these. And then finally, one more, but the actual one. And so basically, this denotes start of workspace. This denotes the actual end of workspace. And then these two guys here denote kind of the beginning and end of an individual tape string. So that's the setup. So this is, I'm going to go from this to this. That's going to be before I do anything else. This is before I start to actually simulate. This is going to be the initialization, just putting all of these triangles here. And there's a lot of ways to do that. And I actually, encourage you to try to do it yourself. Just try to create a subroutine that does this. See if you can. Um, if you do that, if you go ahead and try to do that for yourself, keep in mind, this will help, that this number is going to be the same for any string. The number of triangle patterns you need to do is going to be can be coded directly into the machine. You don't need to add any kind of counting algorithm. You can just create lots of states, right? Because you always just need the same number of tape strings. That doesn't depend on X. So keep that in mind if you decide to do this. It should require like something like K or 2K plus 1 or something states. Okay, so that's what the initial setup is going to look like. And then now we describe how to simulate a single step in general. And of course, if we can do that, then we're done, right? Um, at first, at beginning of the step, at beginning of the one simulated step, uh, we will have this. This is what our string will look like. This probably still won't even be long enough. So I've got this. This will always be here, just to indicate that I should never go left of it. And basically, it's going to have here. I'll have one of these, and then we'll have stuff. And then somewhere in the middle of the stuff, there's going to be like a symbol sigma 1 that'll be underlined. That'll denote the cursor position. Then there'll be more stuff, and then it'll close. So this is the contents of the first tape string. Meanwhile, we have more stuff, sigma 2 underlined. That denotes the cursor position. More stuff, close. And you get the idea. Dot, dot, dot. Um, open up, more stuff, sigma k, underlined, close, and I almost made enough room. And then so that's all k. Oh, wait. Whoops. I forgot to add stuff that's possibly there, right? This is kind of what this is it's one string. We have stuff. This is just kind of the middle of it, wherever my cursor is pointed. More stuff, close, and then finally the end triangle to denote the end. So that's what it's going to look like. I know it's kind of a mess, but you get the idea, hopefully. Hopefully I've explained enough that you can get the idea. Oh, and my cursor will be right here. That's going to be the cursor position. Um, and of course, which represents, just in case you still aren't kind of seeing it, I'll draw what this configuration represents. Uh, Maybe I'll put it over here. So we have stuff, sigma 1, more stuff, and the fact that sigma 1 is underlined means that that the simulation it has a cursor that's here for that string. And then it's all blanks. Maybe I'll just say another triangle, stuff, uh, sigma 1, sigma 2, I should say, stuff, dot, 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 and then the cursor's here, dot, dot, dot. Oops. So that's the idea. So these K tapes are going to be represented like this. This is what it's going to look like in the beginning of a step. It's still K tapes. It's just, on one string. Um, Now, to simulate a step. So to simulate one step, here's the algorithm, and I'm going to describe it in words. I'm not going to write out all of the instructions explicitly. I'm sort of done with that. So scan to the right. Scan all the way to the right. And so I can tell when I've scanned all the way to the right. I can tell when I scanned all the way to the right because I've reached this special triangle symbol. And what am I doing while I'm scanning? Well, I'm looking for these guys. I'm looking for my symbols that are pointed at. So I know what state I'm in. I'm going to be in some state that's going to remember that the associated state that I'm simulating for the original machine. But of course, there's going to be multiple states. I need lots of states to remember gradually and realize which symbols I've found. Um, looking for underlined symbols to determine uh, where the cursors are. Um, to underline symbols to determine where uh, simulated cursors are. And we'll have states to kind of record that information as we go. And if you're uncomfortable with that, then I recommend going back to my alphabet video to look through that. Okay, so we move all the way here. So we move all the way through the string, kind of in a read phase, to figure out what all of the symbols are that are being looked at. And then by that point, I'll know the symbol and the state. But just to make things simple, I'm going to add a step two in which I move all the way back. So step two, move all the way back. That's it. And then step three is now I'm going to move through and change things. So move through again, changing appropriate symbols as needed, and also will have to change which symbol is underlined, right? Because the cursor is going to move on each one of these. If you remember, for a k-string Turing machine, every step, each of these guys moves independently. This could move this way, this could move this way, this could stay still. They're all going to do their own thing, and so I'm going to have to change all of these underlined symbols, or not, depends on what's going on. Um, and obviously there's a question now of how to make space, especially since the simulation starts like this with no space, right? This is the second tape, but there's nothing in between. So we'll have to deal with that, but we'll talk about that. At first though, we don't have to, right? If I have, well, let me kind of say what I mean by that. So maybe we'll have sigma one and lambda, and I've got my tape here. This is the simulation kind of. Well, actually, this is the simulating machine, so this will be underlined. And what I'm going to do as I move through it the second time is I'm going to like change this into like a sigma 2, and that's not going to be underlined anymore because the cursor moved, and now I'm going to like underline this instead. So that's kind of what I'm going to do. It's sort of two steps that makes one step: the cursor position moving and the because I have to change two symbols, so that'll kind of take two steps, but it's not a big deal. Um, Now keep in mind that this lambda could be one of these, so I could end up with something like this. This will be my indication that I need to make space. That's what's gonna happen. Um, and that is what we will talk about now. So step four is move all the way back again. So so basically I move all the way forward, figure out what my symbols are that are being looked at, move all the way back with that information, move forward again now, making the changes as I need to based on that information, then move all the way back again, and now I'm gonna have to make one more pass in order to make space wherever I need to make space. So 5, move through again, um, looking for these guys. These indicate that space needs to be made. That additional space is required um, on a certain tape string. And so what do we do? Well, we get to that point. Let's go ahead and draw it. Um, well, I guess I don't need the end. So let's say, I've got stuff, and then I'm at one of these special triangle right symbols or underlined triangle symbols. I've seen something like this. Use space creating subroutine. I told you this thing was useful. So what's that going to do? It's going to create a blank, and I'm going to actually make sure to underline it. Ah, right. It needs to be an underlined blank because that's where the cursor is. And then this won't be underlined anymore. So it's not entirely using the space creation subroutine. I also need to do a couple extra steps where I underline it and make sure to de-underline this, but that's the idea. So that's step 5, is I move through it one more time and I make space as I move through it. And then step 6, move all the way back one more time. Done. That's it. I've described how to simulate one step. And of course, the machine will halt as soon as, the simulated machine halts. Um, and so that's it. I mean, I did a couple of these rigorously, but you can see, I'm building on all the previous stuff. It seems non-rigorous. A lot of people look at this proof and they would say this is not rigorous enough. It's not real math. Well, the math is hidden because I got really anal about stuff early on. Nothing I've said here is not stuff that I've talked about being able to do before. I can all of this stuff is stuff that I've described how to do in more detail previously, so I don't have to say it anymore. Um, Hopefully, if you've paid close attention to the videos up until now, despite the fact that I didn't actually build the transition function directly, you can see that this is enough. This is completely rigorous. It's perfectly rigorous. So that's how to simulate a um, multi-string machine with a single string machine. So this shows that there's no technically, we have a different model, right? We have a different model of computation depending on the number of strings we have. Same thing with unidirectional versus multidirectional. A unidirectional Turing machine is technically a different model of computation. Same with multi-string Turing machines. If I have if I have a six-tape Turing machine, that's technically a different model of computation than a one-tape Turing machine. And what I've essentially shown here is that all of these models are equivalent to one another. None of them is more powerful than any other. Obviously, to show equivalence, you would have to show obviously that a six-tape Turing machine can simulate a one-tape Turing machine, but I would think that's obvious. Um, so anyway, that confirms that, but there's still a little more to talk about. We still need to analyze the complexity of this, but I think I'm going to split the video here. So because there's a lot to say, we want to be very careful with what we say about that. So in the next video, we're going to talk a little bit more about what we did here, and then we'll be ready to make a universal Turing machine.